Assalamu alaikum. Hi everyone. So today's lesson will be on a design and implementation of a multi-bit adder, or specifically multi-bit ripple carry adder, using Xilinx software and the implementation using the FPGA board. Okay, so let's begin our lesson. So as usual, first of all, create a new project. So name it with a folder name, let's say adder, and then choose the right board, which is the Spartan 3E starter board, and make sure the preferred language is Verilog. Next, and finish. Okay, first of all, we will design a 1-bit full adder. So let's create a new source and name the module as first of all, choose the Verilog module and name it as, let's say, FA. Next, and then as you know, for full adder we have 3 inputs, which are A, B, and C in, and the outputs are carry out and sum. So they are output. Proceed, finish. So we have this. So let's simplify things. Since A, B, C in, all of them are a 1-bit input, so we can combine them into a single line. So we can delete this. Sorry. Then S. So we have this so far. So next, we can write the formula for sum and carry out. So first, assign sum equals to A XOR B XOR C in. Next, assign carry out equals to A and B. Maybe we can put a bracket. A and B, or A XOR B and C in, and place another bracket and save. That's it. So we have done our 1-bit full adder. So we can proceed with the simulations to verify that all these algorithms are truth. So right click, new source, and choose a Verilog test fixture. So we can name it as FA test fixture. Next, and choose this FA file. Next, then finish. Okay, so we have this. So initial begin. So under here we have add stimulus here. So maybe we can remove this, or just command them, command this and command this. So we begin with A equals to 0, B equals to 0, C equals to 0 for a duration 10 nanoseconds, and we proceed. A equals to 0, B0, C1, B0, C1, so should be 1, 1, 1 1 1 1 1 1 1 1 and 1. So save. So here, down here, we can place a finish command so that the simulation will stop until we get this A equals to 1, B equals to 1, and C equals to 1. And save it again. And then we can run the simulation. Go to simulations, choose this file, fa_tf. First, you can run the behavioral check. Oh, sorry, this should be cin carry in and save the file again. Rerun the behavioral check. Everything seems alright, so we run the simulation. So we have two tabs. So click on this tab. So we have this. First of all, you can zoom to full view. Adjust this a little bit. So we have this. So A, B, C's are inputs. So we can relocate them on the top. So we have this. So check all the corresponding output. If A is 0, B 0, C in 0, of course C out 0, 0. And then proceed with this. 0 plus 0 plus 1 is 1. 1, 0 plus 1 plus 1 equals to 2, which is 1, 0. C out 1, S 0. This is okay, this is okay. And finally, 1 plus 1 plus 1 equals to 3, in which 3 equals to 1, 1 in binary. So everything's are okay. So we can close this graph, these windows. No need to save anything. Okay, next. We are going to create a multi-bit ripple carry adder by using this 1-bit full adder. So the strategy is you can create a new source, a new Verilog module, and name this as let's say adder 4. This time we want to create a 4-bit ripple carry adder using the single 1-bit full adder that we just have designed. So next. Okay, so this time our input is A, B, and carry in. So the output is carry out and sum. But this time A and B are 4-bit. So click this. So the MSB should be 3, 3, and S is also 4-bit as well. So 3 down to 0. So we have this A and B are 4-bit variable. C in and C out are 1-bit. S is 4-bit. Next and finish. So we have this the input output declaration. So since A and B are 4-bit, we can combine them as a single line. So we can remove this. So that's it. So next. Again, our aim is we want to use this full adder. We want to recall this full adder into our new file, which is known as adder4. So the method is recall. You can recall the module that you have created, which is FA, and then place a bracket. Inside this bracket, you have to be careful that with the sequence inside this bracket. So first, let's have a look on the 4-bit full adder circuit. So we have 1, 2, 3, 4 full adder. So this should be our Cin, and this one should be our Cout. So remember that we need to recall the FA device 4 times. So far what we have done is we call this FA for the first time. So this FA corresponds to the rightmost F full adder unit. So this full adder unit has 1, 2, 3 inputs and 2 outputs. So the inputs are A0, B0, and carry in, and the outputs for this full adder is the corresponding carry out, which has not been declared yet, and another one should be S0. So first of all, you have to check what is the sequence that you have declared in your FA units. So you have A, B, Cin, Cout, S. So inside this bracket, you have to follow the same sequence. You have A, B, Cin, Cout, and S. But remember that, maybe I can open this side by side. Okay, but remember that this AB is not the same AB in your FA file. This AB should be one of the AB here, and this S should be one of the S in here. Even this carry in is not equals to this carry in is equals, but my mistake. So this carry out is not equal to this carry out, because this carry out corresponds to the final carry out produced by full adder number 4. So for this FA, it corresponds to full adder 1. So its A is actually A0, its B is in fact B0, its carry in is carry N, okay, its S is S0, and its carry out is not our carry out up here. It should be another variable that we should declare later. So sorry. So our A is A0. Use square bracket. Our B is B0. Sorry. Our carry in is Cin. Our carry out should be a different thing. Let's name it as C1. And our sum is S0. And then we proceed with full adder number 2. So you can name this as FA1, and then we have FA2. For FA2, the A is A1, the B is B1. Carry in this time is C1. The carry in for full adder number 2 is the carry out from full adder number 1, which is C1, and then C2, and then S1. And proceed with FA3. A3, B3, C2, C3, S2. Sorry, A2, B2. And finally we have FA4, A3, B3, C3, S3. And this this carry is in fact our Cout. Alright, so let's have a check on all these variables that we have. So to make things clear, maybe we can rename this Cin as C0. So this should be C0, and this Cout is, let's rename it as C4. So we have here C4. Okay, let's have a look. So far, A0, A1, A2, and A3 is already declared here. A and B0, B1, B2, B3 are also declared up here in this line. S0, S1, S2, and S3 have been declared here. C0 is declared here. C4 has been declared as output here. Okay, the only variables that have not been declared yet are C1, C2, and C3. Okay, so the simplest way to declare them is by using wire. Okay, that's it. So all of them, A3 up to A0, B3 up to B0, C0, C4, S3 up to S0, C1, C2, C3, all of them have been declared. So next we can proceed with the simulations. So right click, new source, choose Verilog test fixture. So add for underscore TF. Next. So be careful that you should select the right corresponding file, which is adder4. Next, and finish. Alright, so down here, after add stimulus here, you can declare the stimulus, all these stimulus. So maybe we can comment this first and comment this line as well. So you can proceed. So this time we have how many bits of input? 4 for A, 4 for B, and 1 for C0. Means we should have 4 plus 4 plus 1, 9 bit inputs, and the outputs are 5 bits, which is C4, S3, S2, S1, and S0. So again, we have 9 bits inputs. So how do you want to write the to assign the values for A3 up to A0, B3 up to B0, and C0? So you can use this what do you call primitive way, A30, A20, A10, A0 equals to 0. Continue with B, B3 0, B2 0, B1 0, B0 0, and C0 equals to 0, and for time duration 10 nanoseconds. And you can continue with A3 0, 0, 0, 0, 0, 0, 0, 0, 1. Or maybe we can reposition C0. So first 0, 0, 0, 0, 0, 0, 0, 0, 0. Next 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. And then like here, 1 0, and up to, but we are not going to do this. I just want to show the disadvantage of the current method. This will be tedious and troublesome because you will have hundreds of lines if you wish to choose this kind of assignments. Okay, the other method is, since A and B are 4-bit, you can just write A. Instead of doing this, you can just write A equals to 4-bit binary number 0 0 0 0, followed by B equals to 4-bit binary number 0 0 0 0, and then you can continue. Next, C0, A0 0 0 0, B0 0 1 0, up to C01, A 1 1 1 1, B 1 1 1 1. Okay, but this method is not feasible as well because it requires hundreds of lines. So the more sophisticated way is by using the concatenation or combinations. So if you combine C0, A and B, if you combine all of them and place them side by side, you have 9-bit numbers. So 9-bit binary 0 for C0, 0 0 0 0 for A, and 0 0 0 0 for B. So this this line is equivalent to this. Duration 10 nanoseconds, and you can continue. One and up to 1 1 1 1 1 1 1 1 1. Or you can use the decimal number to represent this binary number. Okay, so you can check what is the value of a 9-bit 1 1 1 1 1 1 1 1 1 in decimal. It actually equivalent to 2 power 9 minus 1, which is 511. Am I right? 2 power 9 minus 1. Yeah, 511. So instead of writing 1 1 1 1 1 1 1 1 1, you can write it using the decimal representation, which is 511. So this is 0, obviously. This is 1. This is number 2. Up to 511. Okay, let's think deeper. Instead of instead of keep writing the same thing all and all over again, why not we place them as a variable? For example, I. C0 A B is equals to I for a duration of 10 nanoseconds. I is in fact a decimal number from 0 up to 511, in which you can use your knowledge that you have learned in your C programming, which is known as for loop. So you can write for I equals to 0, I less than 512, because you can also write I less or equals to 511, but this is also work as well. I equals to I plus 1. Okay, I repeat. For I equals to 0, I up to I less than 512, I equals to I plus 1. Increment 1. Begin. This C0, A0, B0 equals to I. And end. That's it. So this 1, 2, 3, 4, 4 lines represent these 512 lines. So you can remove them. But remember, you have to declare I before initial begin loop. You can place up here. So I is an integer. So integer I semicolon, and finally you can end this loop with finish, finish. But this is optional. It's up to you whether you want to write it or not. So I think we have done everything. So save. Now we can run the simulation. So choose this file, adder for _tf, run the behavioral check, and proceed with the simulation. Okay, so we have A, B, C0, so we can relocate them on the top. C4 and S are output, and this I can be neglected. You can delete it if you like. In fact, this C4 and S can be formed as a single variable. How do you new group? Yeah, choose new group. Let's say answer, an answer. So answer consists of C4 and S. Oh, sorry, it doesn't work. How to combine them? Yeah, new virtual bus. Yeah, answer. Okay, so answer consists of C4 and S. So go to full view and adjust this a bit. Zoom in slowly, so you will have the answer. So let's go. Let's check randomly. So we have 0, 0, 0, 0 plus 0 plus 0, of course, equals to 0. And then let's choose go further. And for example, here. So you have A equals to 3, 0, 0, 1, 1. B equals to 9. So 3 plus 9 plus 0 equals to 13. So 12. So 12 in binary is 0, 1, 1, 0, 0. And maybe you can check the final answer, which is so the simulation has been stopped at 1000 nanoseconds. So you can continue further. Maybe because the simulation is about 512, so change it to 5.12 and rerun the simulation, and you have this. And the last number should be A15, B15, C out 1. So 15 plus 15 plus 1 equals to 31. So 31 in binary is 11111. Okay, that's it. So everything are okay. So now I want to show you how do we implement this module on our FPGA Spartan 3E board. So go to implementation. So we have this adder for, and make sure this symbol, you know, the three squares is located here, meaning that this adder for is currently becomes our top module. So if not, you have to right click and set as top module, but now it is already set as the top module. So click on it. So you will have this panel show the process for our module. You have design summary, design utilities, user constraints, synthesis, implement design, generate programming file, configure target device, and analyze design using chip scope. But not all of them are useful. The first, you have to go to this user constraint. Okay, first of all, we have to create a user constraint file in which we want to do something that you can call as pin assignment. Which input goes to which pin, or in other words, you can say that which pin is assigned to which input, and which LED is assigned to which output. Okay, so if you hold your Spartan 3E board, on your bottom right you have 4 switch: SW3, SW2, SW1, and SW0. On your bottom left you have 4 push button. So you have BTN west, button north, button east, and button south. If you look carefully, your for example switch on your bottom right, SW3, switch number 3, it has its own code, which is N17. SW2 is H18, SW1 is L14, SW0 is L13. So when you want to do pin assignment, you have to refer to this code instead of the name, the switch name. So let's begin. So right click, new source. This time choose implementation constraints file. So you can name it with any name, but normally I name it similar with my module, which is adder 4. But this will be no problem because the format of this file is different. This module is adder4.v, which corresponds to Verilog module. This one is in fact the adder4.ucf. UCF stands for user constraint file. So you will have a blank paper here. So you can write. The way to declare inputs and outputs is by writing net. Make sure it turns blue. And let's say first we want to assign A0. So inverted double comma and then LOC. LOC stands for location. Maybe you can write this as all caps. Let's say my A0, I want to assign switch 3 as A0. So switch 3, the code for switch 3 is N17. Okay, so this line means A0 is assigned to switch 3, which is N17. And then I proceed. A1 I want to assign to H18, which is switch 2. A2 is L14. A0, I think maybe you can do the reverse way. This is A3, A2, A1, A0. Yeah, this will be better. And so A3 is N17, A2, H18, A1, L14, A0 is L13. And then we have B. B3, B2, B1, B0. Okay, since the switch are limited, we only have 4 switches, so we can utilize the push button for B. So let's say B3 goes to push button north, which is V4. You can check on your bottom left, you have 4 switch button. B2 goes to button west, which is D18. B1 goes to button south, which is K17. And B0 goes to button east, which is H13. And save this file. We haven't finished yet. And then we have 5 outputs, which is C4, and S3 up to S0. Okay, the inputs should be assigned to switch or push button, but the output should be assigned to LED. If you look at on the top of switch, there are 8 LEDs from LD7, LD6 up to LD0. So each LED has its own code. For example, LD7 is called F9, LD6 is called E9, and LD0 is called F12. So let's say my S0 is LED0, which is F12. My S1 is LD1, E12. S2 is E11. S3 is LED number 3, F11. And C4 is LED number 4, C11. So we have done with our UCF file. Okay, now leave this aside. Go back to Adder for file. Click on it. So you will see this user constraint, and you can proceed with the synthesize. So double click on this. So it will run the process step by step. You have to wait a little bit. Make sure the green tick symbol appears, meaning that everything is alright. And then you can double click on implement design. So this translates map so far are all right. So we are waiting for place and routes. So everything's are okay. So next, go to generate programming file. Double click on it. So this step will generate a programming file which is known as .bit file that we will see later. So here. Okay, so we have under configure target device, we have two sub menu, which is generate target PROM/ACE file and manage configuration project, or the short form is known as impact. So you can turn on your FPGA board, plug in everything, and turn the switch on. So make sure your computer detect the connectivity. Okay, so maybe you can launch this impact menu. So you will have this windows. So double click on boundary scan. Okay, right click here and choose initialize chain. Click yes. Okay, as I mentioned before, a .bit file will be generated. So choose it. Choose header for .bit file. Open, and you get this message dialog box. So what is this? So maybe no. So you can click bypass. Okay. And the final step is right click on this and choose program. Make sure you get this message, program succeeded. Okay, now you have completed the what do you call download. You have downloaded your module onto your FPGA board, or you can call it burn. So you can test. Okay, I forgot one step. Maybe you can close this. Okay, normally for push button, we need to declare the pull down, PULLDOWN, pull down. Write this, declare pull down for every push button, save them, repeat the process. Pull down means you have to press the button to get high input. So generate again the program file. Okay, relaunch impact one more time. Double click on this, right click, initialize chain, yes. Go back to impact Windows, initialize chain, choose this, open, no, bypass, okay, right click, program. Okay, that's it. So you can try the inputs by pushing the push button and trigger the switch. Okay, make sure, for example, if you want to try 4 plus 5, press the right button and choose the right switch, and make sure the answer displayed by the LEDs are correct. So that's all for now. So hope you can get the successful results. Good luck and see you next time. Thank you.